Let's see, our next speaker is Trevor Weiss from New Mexico State. He's going to talk today about asteroseismology and the Galactic Bulge time domain survey.
Thank you very much for having me. Again, my name is Trevor. I am a first-year graduate student at New Mexico State University, and today I'm going to be talking about results from a published paper myself and my co-author Noah Downing published back in July 2025 on the asteroseismology of red giants within the Roman Galactic Bulge time domain survey. Additionally, I'll be presenting on some updates from those results, along with work going on within the Roman Asteroseismology wide field science team that is PI'd by Mark Pincinel at Ohio State. Something really cool real quick to show. This is, oops, sorry, wrong button. There we go. This here was a pretty cool thing to do. Myself and Noah contributed to a STSCI press release about the seismology of Roman. And if you have the chance to check it out, this is actually from a video that kind of shows the sonification of stars, which I always think is really cool to hear the internal composition of stars wise, so kind of fun thing to do with that. But yeah, as many of you know here, the Galactic Bulge time domain survey is going to have that 12-minute cadence. There's also be 4 seasons during the off-season here with 3-day cadences as well. Keep pressing the wrong button, there you go. They also have the 0.11 arcsec pixels for photometric and spectroscopic observations of stellar characterizations and temperatures. There's going to be a wide field of sciences that you're going to be able to do with the Galactic Bulge time domain survey, from microlensing and translating exoplanets to understanding the formation history of the galactic bulge. Something that we're particularly interested in are the stellar populations within the bulge, and more particularly trying to settle this discrepancy between stellar age distributions within the bulge itself. So right now there's kind of some competing understandings of stellar age distributions. There's some studies that show that there's a more uniform distribution, shown in the red here, from 2 gigayears all the way up to about 13 gigayears for the ages of stars. There's other publications that showed there's a much more concentration on the older age of stars here. The issues with these surveys is that there's a very limited population that you're able to actually get information of stars from. These are a lot of, I think both of these samples are from a handful of white dwarf stars on the edge bulge. And so we kind of are looking to try to resolve this discrepancy with a much larger sample, which better constraints the uncertainty of ages within the stars of the bulge itself. And so how exactly do we get the measure of stellar ages in the bulge? That'll be through asteroseismology. So I think Maddie did a fantastic job explaining today. You know, no coordination at all with that for the most part, surprise with that. But just to kind of briefly through it, since Maddie's already done a great job with that, is this mass relation you can get from asteroseismology, measuring its max frequency here up top, and using the large separation between peaks within seismology, within the oscillations, called delta nu here, to get this mass relation here, in which then you can get your stellar ages with the inclusion of effective temperature. And so with Roman and Galactic Bulge time domain survey in particular, its cadence, its pixel count, it's going to do wonders for asteroseismology as a whole. And that was kind of the basis of the work that we did for the paper that we published back in July. So first off, I want to go over the modeling of actually getting these asteroseismic detections. Unfortunately, I can't go too much into detail just based on time constraints, so I highly recommend you read the paper that we published right here in the QR code. And this is mostly work done by Noah Downing, now a PhD student over at Yale University. But I think this plot here kind of is very telling in the sense of this is a Kepler object with its power density and frequency here. The red line here indicates its new max point. The green is Kepler. This is the measured Kepler object. And Kepler, again, is kind of the golden standard for asteroseismology. The 15,000 candidates have very strong oscillation peaks that we can very easy to identify and measure. And this blue line here is going to be the simulated Roman power density plot here as well, and its max frequency. So this includes its noise, the cadence from Roman, and this also takes into effect the dampening effect of the amplitude from IR. And as you can see here, it is still within exactly what we're looking at for new max detection here, slightly lower, but it is still very measurable and readable. So Roman, as we've proven from the paper, is going to be able to get these resolved measurements. And again, I'm happy to discuss more later on the talk-wise after questions. But going through the modeling, we then went ahead and did a synthetic survey and applied this detection probability method, again, read the paper for that, to try to see how many objects we're actually going to get astroseismic measurements from. So from our results, we estimated roughly about 300,000 astroseismic red giants and red clump stars, about 200,000 of them in the bulge. I should emphasize that this is our conservative estimate. We have upper limits of upwards of 700,000 detections in total and roughly 500,000 detections within the bulge itself. I will show a later slide to kind of show how this compares to other astroseismic missions. Additionally, about 50% of the total detections will be able to be identified within the first 70 days of observation. So you can see here on this HMAG plot here, the comparison between the first season and the full cycle 1 season of measurements with the Galactic Bulge Time Domain Survey. I have a slide later on to discuss the saturation and semi-saturation limits as well, so don't be concerned by that. Additionally, you can see here our peaks here with stellar radius and the population bins. This peak here being a lot of the red clump stars. So roughly we get about half red giants and half red clump stars within the Galactic Bulge Time Domain Survey mission for astroseismic measurements. So asteroseismology has been used in missions like Kepler, K2, CoRoT, and TESS, and you can see those totals here. So if our conservative estimates hold up, along with that 50% within the first 70 days, we expect to have as many detections of asteroseismology within the first 70 days of Roman as Kepler, TESS, and CoRoT all combined in their entire lifespans, which is amazing to do. Oh, sorry. Perfect. And additionally, none of these studies have actually looked at the bulge itself. So here is a plot showing the relative location of astroseismic detections from CoRoT, K2, Kepler, and TESS, and the simulated expectations of Roman detections here as well. And you can see their distances up here. And again, this will directly contribute to models of the galactic bulge and getting that information about bulge modeling and bar modeling as well. As you can see here, these top two plots are from Dan Hayes' paper from Ogle data of stars, and these right here are our simulated plots here of astroseismic detections. The green circle denotes the galactic center, so we'll have a significant sample of galactic center objects that actually have measured asteroseismology as well. And again, will contribute to models for bulge and bar of the galactic bulge in the Milky Way. Additionally, within our synthetic survey, we applied a age-metallicity relation based on Meredith Joyce's work. I had shown that slide previously of the stronger concentration of older stars. So we had shown that we had incorporated those stars within the synthetic survey analysis. And you can see here a tail, pressing the wrong button. The tail of metal poor stars will actually get able to get measurements for. Some of these stars will be some of the older stars, and the hope would be that we actually be able to resolve that and find some members of globular clusters as well, as Maddie we're hoping for as well with that. Additionally, we included some constraints with extinction between Marshall and Slagle maps, and we found that the extinction maps were fairly marginal between those two in our overall yield counts with that. Now, as mentioned before, what about our stellar ages? So I had shown previously that relation using nu max, delta nu, and effective temperature in order to get this infer mass, and from mass then we can infer stellar ages for our sample. Roughly 30% of our sample are going to have resolved delta nu. Delta nu is a bit harder to resolve itself. The amplitudes and seeing those separation of modes require a bit more work. So roughly 30% of our sample would have resolved delta nu, which is good for galactic chemical evolution models, but we want the full sample if we can. So what we can then relate to is getting a parallax. So with parallax, we can use the Stefan-Boltzmann law to get a luminosity, get effective temperature to solve for our radius. We can then solve for radius and use this relation here, including nu max, effective temperature, and radius to get our mass. And in fact, using parallax itself will get us a stronger uncertainty at ages of around 50%. For reference-wise, with red giant red clump stars, you get about 100% uncertainty with isochronal data, and you get about 40 to 60% uncertainty with photometric data. So this really is going to do wonders for resolving those age uncertainties and actually be able to separate our red giant red clump populations from intermediate ages to older ages as well. And all objects with NUMAX will have parallax, which is more precise at measuring stellar ages anyways. So just to kind of go into other work that we're doing, Lauren James and Joel Zinn at Cal State University Long Beach are currently working on a saturation pipeline. This is for differential photometry. It's possible either at PSF agnostic, weighted photometry method, or aperture photometry. Additionally, you can see here with our noise floor that a lot of these objects here from the bulge itself will be able to have astroseismic detections from that. I highly recommend you look at Lauren's poster, who she's here today and has a poster out there, poster 13, I believe. She can go into much further detail on the current work with the saturation pipeline. I'm sure a lot of people here are very interested in that. Additionally, work done by Maddie Howell, Adam Ballas, and Mark Pinsino at Ohio State. They're currently working on creating a real target list of red giant stars that are potential candidates for astroseismology. This is using VVD data and 2-mass data cross-meshed with a Gaia DIA4 release. And we find that roughly about 500,000 potential objects in the bulge are going to have astroseismology, and these are red giant and red clump stars. In particular, the significant number of red candidates are red clump stars, which will serve as a calibration sample for any newly discovered objects that we get. Very quickly, here are our key takeaways, but I actually want to quickly highlight this future work that I look to do. Again, I'll be starting at New Mexico State in the fall, and that enables me to be an STS member. With the large number of astroseismic detections we're expecting, I think there's going to be a nice overlap of getting chemical abundances through apogee and using the SDSS data. And so that will be with the after-sonified Hidden Galaxy Explorer. Specifically, as you can see here in this plot, it's going to have a perfect overlay with the Galactic Bulge Time Domain survey looking at the bulge and objects past the bulge itself on the other side of the halo. And so this is going to be really good work in regards to, if anyone knows about the APOCAST data set with astroseismic ages and chemical abundances and how useful that's been, this will potentially provide a sample of an order of magnitude 2 greater than the APOCAST sample. So a much larger and detailed sample set that we would have of astroseismic ages and chemical abundances in the bulge itself. And with that, I will go back to this slide and answer any questions.
Okay, what questions do we have today? Thank you very much for a great talk. You got Robbie Longy.
Hey, Trevor. What wonderful talk. I'm curious about your last slide, and for stars on, the other side of the galaxy. What does the sample look like? Is it like high, very luminous red giants above the red clump, or what?
So that sample-wise, we actually get distances from our simulation of astroseismic detections up to about 250 kiloparsecs, and that is well within the other side of the halo for those objects. These are going to be very luminous red giant objects, not necessarily red clump objects. And on a scale of population size, these are going to be more on the individual basis. These aren't going to be the 200,000 that we detect within the bulge itself, but more closer on the roughly 4,500 astroseismic detections based on early simulations. So not necessarily enough to classify a population within the halo itself, but more interesting to find individual targets and objects that we'd be able to find in the other side of the halo.
Okay, any other questions? Any questions online, Tiffany? Oh, there we go.
Great talk, thank you. I was curious about individual mode IDs with Roman. Is it kind of around that 30% that you mentioned for Delta Nu, or do you have any estimates on mode IDs?
Right here. So I'm glad you asked this, one of my supplemental slides. So mode IDs wise, again, as you can tell, they're going to be a little bit noisier. As I mentioned, roughly 30% of our sample are expected to get Delta Nu detections, which include those mode IDs. So for better understanding for Delta Nu, it is more of a characteristic of the internal density of a star itself. Again, it's not necessary for us to have Delta Nu in order to get those astroseismic age uncertainties. But there is going to be a significant sample of our detections that will get those Delta Nu modes resolved. And you can kind of see here some examples of a shell diagram of what a shell diagram and a relative power frequency plot to kind of show what those modes would look like in relation to Roman detections. But happy to discuss more afterwards as well.
Okay, thank you very much, Trevor.